In this video, we'll examine compound interest, which is when interest accrues on old interest, as opposed to simple interest where the interest accrues only on the principal. So our main formula is pictured here. P sub n, that's the future value of the money. That's what you will have after all the interest is accrued. P sub 0, or P naught, that's the initial investment or principal. R is the interest rate. K is the number of compounding periods per year, and capital N is the number of years. So we'll investigate this formula by using a few examples. So for our first example, let's say we deposit $75,000 into an account. It's a compound interest account and it accrues 8% interest, and the compounding period is quarterly, which means it compounds 4 times per year. So the question is, how much money will you have after 5 years? And for that, we go back to our initial formula, which is the thing that we had on the previous page. So that's P sub n equals P naught times 1 plus R over K raised to the n times K. And now it's up to us to figure out which of these variables correspond to which numbers in the problem description. So the first thing I notice is it says, how much will you have? Which indicates that we want to know how much money will we have in the future, so that's solved for P sub n. We want to know the future value. So we will start by just saying P sub n is our variable, and that's what we want to solve for. P naught is the initial investment, or the principal, so that's $75,000. 1 plus R is our interest rate, so that's 0.08, because it's 8%. Compounded quarterly means that K equals 4, because quarterly means 4 times per year. So the number of compounding periods per year is 4. Capital N is 5, because we want to know after 5 years how much money will we have, and then that's times 4, which is K. So notice this exponent 5 times 4, that's the number of years times the number of compounding periods per year, so that's the total number of compounding periods that will occur. And all that's left is to plug this stuff into a calculator and get the answer. So when we plug some of these in, I'm going to approximate some of these. So we'll have 75,000. The easiest way is probably to work from the parentheses outward, and so if you plug in 1 plus 0.08 over 4 into your calculator, you get 1.02. And then 5 times 4 is 20. So we have 75,000 times 1.02 raised to the 20. And so now we need to start approximating. So I'm going to switch my equal sign to this approximation symbol. So I'm going to have 75,000. And if I raise 1.02 to the 20th power, I get roughly 1.48595. And of course that's rounded. You can choose how many decimal points you want to go out to. And then finally we'll multiply these together and we get roughly 111,446.05, which is also an approximation, but I cut it off after 2 decimal points because it's money, and so we just need it accurate enough down to the cents. So this is our answer. So how much money will we have after 5 years? $111,446.05. Okay, so let's look at a very similar problem. We're going to take the same account, same initial deposit, same interest rate, but instead of compounding quarterly, which is 4 times per year, we'll say this account is compounded daily, which means every day interest accrues. And the same question, how much money will you have in 5 years? since it's the same style of question, we use the same formula. So in this case, we still want to solve for p sub n. We still invest $75,000 initially, and our rate is still 8%, but now our k value has changed from 4 to 365, since we're compounding daily as opposed to quarterly. We're still leaving it in for 5 years, but we're compounding 365 times each year. So at this point it becomes a very similar problem to the one above. We approximate, plug all this stuff into a calculator, we get an answer. So I'm just going to show you the way I proceeded. This is a pretty bad decimal that we get in here. It's 1.3 zeros, 219, 178. And then 5 times 365 is 1,825. And also this is an approximation, so this should have been approximation. So then I'll do the exponentiation, leave the 75,000 alone, and we get roughly 1.491759. And then finally multiply these together. So we get 111,881 and 95 cents. So that's our answer. And notice in these two problems we get different answers. We had the same initial investment, same 8%, same 5 years, but the compounding period was different. And notice if you compound more often, you end up with more money. That's the nature of compound interest. Okay, so notice in both of these problems we had to solve for p sub n. That's not always the case. Different types of problems require different types of uses of the same formula. So let's take a look at an example where we need to solve for time. In other words, we need to solve for capital N. So here's our situation. We invest $10,000. Our account's compounded monthly, so that tells us that k equals 12. And now we have a 5.5% interest rate. And the question now is, how long will it take that $10,000 to grow to $18,000? So again, we use the same formula. Pn equals p naught times 1 plus r over k raised to the n times k. And again, we just need to figure out which variables correspond to which numbers. So this time I know p sub n, that's 18,000, because I know how much money I want to end up with in the end. And I know how much I invest, that's 10,000. I know r, that's 5.5%, so that's 0.055. It's compounded monthly, therefore k is 12. But what I don't know is capital N. And so this is what my equation looks like, and I have to solve for n. So in this case, it can get a little messy when you get into the arithmetic. So what I want to do first is get this term that has the n by itself. So I'm going to take this 10,000 over to the other side, and I get 18,000 over 10,000. Everything else over here stays the same. But the problem now is this n is kind of trapped in the exponent, and I need to get that out. So the way I get exponents out, the way I undo them from being exponents, you could say, is by taking natural log, or logarithm base, whatever you want to choose. So I'm going to choose natural log, and we have to take natural log of both sides. And I'm also going to realize that 18,000 over 10,000 is just 9/5, so I don't have to write all those zeros. And so we have natural log of this whole thing. 1 plus 0.055 over 12 to the 12n. And the magic of exponents tells me that on the right hand side, I'm going to leave the left alone for now, this exponent gets to come out front. And this is a property of logarithms. This exponent can be factored out front. So this becomes 12n times natural log of what was the base inside. And now my variable is out here and it's multiplied instead of raised as an exponent. Therefore I can solve for it. So if you divide everything over to the left besides n, you get natural log of 9/5 divided by the 12 comes over, and the natural log of 1 plus 0.055 over 12 comes over. So this is kind of sloppy writing my equal sign like that. And actually we can count this as our answer. Most likely if you're using this in the real world, you want a decimal approximation of this. So just in case you're curious, if you were to plug all this into the calculator, you would get roughly 10.71. So what that translates to in terms of our problem is, remember we wanted to answer this question: how long will you have to wait for that $10,000 to become $18,000? You have to wait roughly 10.71 years. That's the units. So after 10.71 years, your $10,000 becomes $18,000. Okay, so that's solving for time. That's fairly involved. What about solving for rate? So let's say we have this situation. You start with 10,000, you want to grow it to 18,000 again, but this time instead of waiting as long as you have to, you have a fixed amount of time. So let's say you only have 5 years. That's how long you can take to grow this money. And the account is compounded monthly, but now you need to get the proper rate in order to grow 10,000 into 18,000 in the constraint of 5 years. And so we still use the same formula. And after we plug in all the stuff we know, 18,000 is what we want our money to grow to, 10,000 is our initial deposit, R we don't know, K is 12 because it's compounded monthly, N is 5, and again K is 12. So now we have to solve for R, and this algebraically will be even worse than the problem before, because now our R is buried within this exponent. So we're going to use kind of a mathematical trick. So the first thing I do is I take the 10,000 over, and remember that was 9/5. That's 18,000 divided by 10,000. So I have 1 plus R over 12 raised to the 60. That's our 5 times 12. And I kind of want to get rid of this 60 because that's causing problems. That's not allowing us to solve for R right now. So what I'll do is take natural log of both sides again. So natural log of 9/5 equals, remember if we take natural log of the right hand side, the 60 factors out. So that's natural log of 1 plus R over 12. And I'll get rid of this 60. So we have natural log of 9/5 divided by 60 equals natural log of 1 plus R over 12. Okay. So at this point, the R is now trapped within a natural log. And so we need to get that out. So what I'll do is, first of all, it's going to make it easier if we get a decimal approximation of this left-hand side. So I'm going to use an approximation, which means I need to switch to approximate. And if you plug in natural log of 9/5 divided by 60 into your calculator, you get roughly 0.009796. And then we still have our natural log on the right-hand side. So what I want to get rid of is this natural log, and the way I do that is I raise each side as an exponent of e, which is the base of the natural log. So I'm going to make a note of that. That's the number e, not the letter. So I get something like this. E to the 0.009796 is about e to the natural log 1 plus r over 12. And just like you could factor out exponents outside of natural logs like we did up here, this is another property of natural logs. If you have e raised to the natural log, the e and the natural log cancel out. So you're left with just 1 plus r over 12. So from here to here, that's a property of natural log. And this is just a number over here. So now all that I have left to do is solve for r. So if you plug in this e raised to the 0.009796, then you get roughly this. .009845. And so that is our 1 plus r over 12. And the rest is fairly straightforward. So you subtract the 1 over, so you get 0.009845, and that's r over 12, and then multiply both sides by 12, so you get r is about 0.1181. That's our answer. So it's a fairly involved process. Oh, sorry, you couldn't see that. And remember, r is an interest rate, so that's about 11.81%. That's the interest rate that we would require to grow $10,000 to $18,000 in 5 years, compounded monthly. And if you want to check your answer, this isn't part of the problem, but if, say you wanted to check, because this required a lot of work, so how do you know that your answer is correct? So to check, you can just plug in. So you get back to your original equation, P sub n should be 18,000. We'll pretend like we don't know what it is. And so that should be your initial investment of 10,000 times 1 plus your r that you just found, so that's 0.1181 over 12 raised to the 5 times 12. And you should be able to plug this into a calculator and get 18,000. So we're not going to go through that, but know that if you don't get exactly 18,000, it's probably just rounding error, because we did, starting at this point, everything's approximate, which means we had decimal points missing. So anyway, if you plug this in to check your answer, if you're off by a few dollars, that's okay. It's just rounding. So just to recap, we had our initial formula. Our main formula for compound interest, and we've seen how to solve for P sub n, we've seen how to solve for r, for n, We won't worry about solving for k. If you want to solve for p naught, it's basically the same as a piece of n type problem. And that's how I use the compound interest formula.